Hello and welcome to Paris, home to the Eiffel Tower, the Louvre and the grave of Eugène Anatole de Marsay. Unknown as he may be, this remarkable Parisian contributed to the discovery and isolation of several elements back in his day, the most remarkable of which we're talking about today, and that's europium. It is the 63rd element on the modern periodic table due to its protons, each complemented by an electron. Tallying that up gives an outer shell of 7 4f electrons and 2 6s electrons. At room temperature it's a solid, soft, grey-silver metal. De Marsay probably sourced his raw material containing the element from India. Nowadays the biggest rare earth element exporter in the world is China, thus also of europium. Now, De Marsay's profession as a spectroscopist and inorganic chemist led him to suspect the existence in 1896, and he managed to isolate the element by 1901. Luckily for him and us, europium has luminescent properties, being part of the lanthanide series. The most common form of europium, its oxide, emits a pure red light after excitation. To be complete, this is europium with a 3+ charge. The less common 2+ form also exists and emits blue tints of light. Europium is particularly useful because of its efficient excitation. This makes it the preferred material to use as dopant for phosphors. Basically, this means that it's sprinkled through other material to get the desired color. Because of this last property, it became wildly popular with the introduction of cathode ray tubes. Even though they have been replaced by other television technologies, europium still has plenty of uses. For instance, it's used in fluorescent lamps and some LED lighting. Another use is in sodium lamps to get the light from yellow back to something more akin of white. Yet another use is in euro banknotes. They contain, among others, a security mark with europium 3+. As with everything, you can't have upsides without downsides. Although China only has roughly a third of rare earth element deposits within its borders, it exports 85 to 95% of the global demand. This is due to low prices because of state-backed companies. As is expected, much of the world is dependent on China for all its rare earth element needs, because all competitors are swiftly driven to bankruptcy. And the mines aren't exactly a treat either. The elements are found in minerals as bastanite and monazite, and in low quantities. The mines are therefore usually surface mines, where tons and tons of material are removed and taken to purification facilities. Also, a process of leaching has been used, which is the act of letting water or fluids flow through the ground and retrieve the desired materials in the water on the other side. Needless to say, this leads to pollution of the surrounding surface water if done incorrectly or unsafely, and it doesn't need remarking that this is often the case. The waste of rare earth elements is hard to deal with. Studies from the United Nations University and World Health Organization suggest that the waste from mines and landfills of electronics have impact on child health, raise concern around chemical burns, cancer and stunted growth. After its use in appliances, europium is quite tricky to separate again. This and the low market price of rare earth elements prevents recycling from becoming cost effective, even if it's one of the most important ways to lose dependency on the suppliers. Nonetheless, research has already demonstrated that there are a few ways to get back the material reliably. In general, about 38% of europium can be won back after use, EU research states. For a rare earth element, this is exceptionally high. For tube-light phosphors, the percentage can be even as high as 60%. But how? Well, for phosphors, the mix of elements is mixed with hydrochloric acid and then is run through several baths of separating liquids. The step determining the maximum yield is an acid treatment with D2AHPA. This gives a good separation between the europium and the yttrium present in the phosphor. With Europe looking for ways to become more independent from other countries, you might see this being realized within the EU. Now keep in mind it will not be enough to fully replace the mining of the material, but it will reduce the reliance on it. Another option for reducing the import of europium is to find another material to replace it with altogether. Different materials are current subjects of research, like perovskites and quantum dots. Perovskites, in the sense of metal halides, are only stable for relatively short timescales. Cadmium dots have their own environmental challenges, and carbon dots tend to also be too unstable. But research into improving these options and looking at other alternatives is still ongoing and may give the answer in a few short years. Now that's all good and well, but where does that put us? Currently, there is still much Europium being imported yearly, mostly for lighting purposes. Recycling trials should be scaled up quickly in an effort to save the Europium from discarded lights. Parallel to that, the research continues for less costly alternatives. Not necessarily completely without Europium, but maybe just a bit less. As for Eugène Anatole de Marsay, he helped us get to a place where the money is a bit better protected and the street lamps are a bit better colored.